So as we're reviewing for linear regressions, the first question says, researchers studying growth patterns of children collect data on the heights of fathers and sons. The correlation between the heights of the fathers and the heights of their 16-year-old sons is most likely to be, well, it can't be greater than 1. It will never be exactly 1. I mean, that's almost ridiculous to think, nor would it be a negative correlation, because as the father's height increases, so should our son's height, okay, because we're all doing it at the same time. As one gets larger, the other should get larger. Near 0, no. I mean, that's saying there's no correlation whatsoever. And it is genetics. There is some involved. So looking at all these, C makes the most logical answer. Okay, the auto industry crashed some of its test vehicles into a barricade, and at speeds of 5 to 25 to investigate the amount of damage to the car. They found a correlation of 0.6 between miles per hour and damage in dollars. If the speed of the car hit the barriers 1.5 standard deviations above the mean speed, we expect the damage to be, okay, my correlation is 0.6. The standard deviation is 1.9. So if I can get a clear picture of the calculator here, we simply say 0.6, the correlation, times the standard deviation of the other gives me the response for this one to be about 0.9. So this answer would be D, about 0.9 standard deviations above. It's not going to be like the regular standard deviations of this to this because my correlation is only 0.6. Okay, a scatter plot shows a strong association even though the correlation is probably near 0. Okay, let's look at which one's correlations would probably be near 0. This is a positive correlation that is probably above 0.7. This is a negative correlation that looks to be probably really close to a negative 0.9. Okay, there does seem to be some correlation here. Now there's a lot of scatter there, but there's a fairly strong, consistent growth to that. There's no correlation. I mean, that's a true scatter plot. So, but the correlation might be near 0, but there doesn't seem to be a strong association. So this one makes sense. There seems to be a strong association. There is a pattern to them. There is a consistency to what's happening. It's going up as a group and then it's coming down as a group. That association is strong, but the correlation, line of best fit, will probably be very similar to what we did with our class activity. So the answer on this one is C. Okay, so the correlation between X and Y is 0.35. If we double each X, decrease Y by 0.2 and interchange the variables, I've already told you the answer to this one. We put the X on the Y and vice versa, the new correlation is still going to be 0.35. Okay, it's not going to change anything. That is still slightly confusing to me, but that's just me. Most of you probably understand that. Okay, a consumer group collected information on HD TVs. They created a linear model to estimate the cost of the HD TV, high definition, based on the screen size in inches. What is most likely value of the slope of the line of best fit? Okay, in other words, as the screen increases by 1 inch, the cost of the television probably goes up by, and you can see that I marked 70. Now, some people might argue 700, and I could probably live with either of those two answers. They're assuming pretty much it's kind of 70 bucks an inch, but either of those are fine. That could be C or D is what I'm saying. All right, and then on number 6, the correlation between a family's weekly income and the amount they spend on a restaurant meal is found to be 0.3. Very low correlation. So what must be true? So there's not a high correlation. That means it only happens part of the time. Families tend to spend about 30% of their incomes in restaurants. No, that's not what this says. Okay, there goes that approximation again. In general, the higher the income, the more the family spends in restaurants. Yeah, that's probably a true statement. I know it is with the brothers that I have. The two brothers that make a lot more money eat out more often, and those of us that don't make as much money, we eat home more often. And then it says the line of best fits through 30% of the data points. No, we've seen, data point, we've seen line is the best fit. They don't touch any of the data points. So no, it's not going to be 3. The only one it might be, since there's not a none, it'd be 2 only. So that's going to be B. Of course, I guess it helps the fact that I have all these letters written out here already. Okay, a medical researcher finds that the more overweight a person is, the higher his pulse rate tends to be. In fact, the model suggests that 12-pound differences in weight are associated with a difference in pulse rate of 4 beats per minute. So which of those is true? Okay, as you can see, the answer is going to be 3 only. The correlation between pulse rate and weight is 0.33. Nope, they just divided this by this. Don't do that. Don't do that. That's not how we find the correlation. If you lose 6 pounds, your pulse rate will go down 2 beats per minute. Maybe, but there's no guarantee on that. A positive residual means a person's pulse rate is higher than the model predicts. That's the only statement that is absolute true. That's the reason why the answer for this one is D. Okay, number 9. A regression analysis of company profits, the amount of money the company spent on advertising is R squared is 0.72. It's R squared, R squared. So 72% of the variability in the amount of money spent or company profits can be accounted for in the variability of the amount of money spent for advertising. But none of these say that. This model can predict the profits for 72% of companies? No. This, on average, about 72 result from advertising? No, that's not what it's saying. On average, companies spend about 72% of their profits on advertising. It doesn't say that either. Okay, that's not what the R squared means. This answer is none. It means that 72, it's the coefficient of determination, about 72% of the money spent on advertising can be accounted for, or about 72% of the profits can be accounted for in the variability of the amount spending. Okay, number 10 here. So least squares regression line is fitted. Here is the residual plot. Great residual plot, agreed? So the linear model is appropriate. Yes. Oh, it says the linear model is poor because some residuals are large. Doesn't matter. The linear model is poor because the correlation is near 0. That's not telling us. It's a residual plot. A curved model would not be better. So the answer is A. A linear model is appropriate. And remember, what's the sum of all those dots from the distance of that line? Thank you. It is 0. Okay, for part 11, we're going to need a formula page. Where is my formula page? There it is. And on the formula page, it says college job placement collected data for students' GPAs and salaries they earned in the first job after graduation. The mean GPA was 2.9, standard deviation of 0.4. The starting salaries had a mean of $47,200. Wow, good for them. With a standard deviation of 8,500. Wow, that's large. 2 standard deviations below that is what, $17,000? So only $30,000. And another standard deviation, anyway. The correlation between the two variables was 0.72. So it's high moderate. The association appeared to be linear in the scatter plot. So it says write the equation of the model based on the GPA. Okay, so here's the model we're looking for. And this is how these two we're going to use because we need to find my slope, our mean rate of change. To do that, we take R, the correlation, which was 0.72, times the standard deviation of Y, which is the 8,500, divided by the 0.4, sorry. So I've written that here, 0.72, 8,500 divided by 0.4. That ends up being 2.9. Nope, no, it doesn't. That ends up being, oh, where'd that go? I thought I wrote that in there. Hang on just a second. Sorry about that. So 0.72 times 8,500 divided by 0.4 is 15,300. So this number is 15,300. So then we plug those in to solve. We need to find our y-intercept. So we have 47,200. This is all algebra, folks, minus, 15.3 times 2.9 These are my means, the mean GPA, the mean starting salary. That's 2830. So A is 2830. So our equation, let me find my pen, becomes this. Salary hat equals $2,830 plus 15,300 GPA. Kind of makes you want to do that. Do you think these predictions will be reliable? Okay, our R is 0.72. So it's high moderate. The R squared is 0.52. So yeah, we could feel somewhat comfortable with this. Okay, your brother just graduated from college with a GPA of 3.3. He tells you that his residual is 1880. What is his salary earning? So we plug back in our number. We do 50, and his value ends up being 51,440. In other words, we take the residual. We have to first predict his pay. We got to plug in 3.3 there. So 2830 plus 15300 times 3.3, enter. We do expect 53,320. Okay, and then we subtract 1880 from that, and we get 51,440. Put my dollar sign in there, sorry. Okay, number 12. So we work on an assembly line. This is the weeks, and this is how quick someone's getting. The faster they do, the faster they learn how to do it. We're assembling camcorders. This is old. As you get faster, the more you do it. The company tells you qualify for raise in 13 weeks if your average time is under 20 minutes. The data shows each assembly during the first 10 weeks. Okay, which of these is the explanatory variable? Okay, the explanatory is my independent. This is my explanatory variable. This is my response variable. The correlation between these two variables is a negative 0.968. To do that, let me see if that's, did I put it in this calculator? Nope, not this calculator. Let's look over here in this one. No, that's all of those. Oh well, I wonder where I put those numbers. Anyway, L1, L2, plug it in, run the correlation, get a negative 9.968. Now the question is, should we do whether it be appropriate for a linear model? And the answer is no, because the residual plot. And hang on, and I will show you the residual. So we have our numbers, and I've got them in L3 and L4. So I'm going to turn this scatter plot on. Oh, no, I'm going to turn this one off. It's already off. I want to go to 2. And turn this one on. Here's L3 and L4. And now I want to go stat and calc 8 for L3 and L4. Well, I need to go back to y equals. I'm going to clear that one and clear that one. I have no idea what those were to. Okay, so stat calc 8, L3 and L4, and I need to go vars, y vars, enter. I'm going to put it in 2 just for something different. Okay. So there's a negative 90.97 for my R. R squared is 94. There's my equation. For 42 is my initial value. It's how many minutes we would expect for 0 minutes. And my slope is that as a negative 1.812, 1212, whatever you want to call it. So we would assume that for every week of work, our time would decrease on average by negative 1.82. 1.812, sorry. So now let's second y equals, and let's go here. Oops, nope, let's go here. And I'm going to change this to residual. So second stat to go to residual, type 7 there, and then zoom 9. Okay, is that a true scatter plot? The answer to that is no. Notice there is a pattern to it. It comes down and then it kind of goes up. So is this a good linear model? And the answer to that again is no. And I would show the residual plot. The residual plot shows a pattern. I would print the residual plot here, just whichever. Okay, I hope that helped.